Hello. In this short video, I'm going to solve a problem using an extended flow state test calc. The background for this are found in chapters 0, 1, and 3 that explains what is a flow state, what is an SL model, etc. So let's begin with the problem. Here we have a pump. State 1 is the inlet and state 2 is the exit. And some information, different properties are supplied at state 1 and 2. And we are supposed to find the change in the rate of transport of flow energy. How much energy is flowing in, how much energy is flowing out, the difference between the two, and the contribution to that because of pressure has changed, because temperature has changed, etc. So we begin by launching the appropriate test calcs. For that, I've already logged into thermofluids.net, and then we click on the test calcs module. That takes us to a page that gives a description of different test calcs that are available. We are looking for the flow states module. As you put the pointer over the description appears, we click there. That takes us to a page where different material models are offered. A flow state calc can involve different kind of fluids. In this case, liquid water is described by SL model, the solid liquid model. We click there, and that should take us to the test calc page. You'll notice there are 4 different tabs. Here the solution will appear right here, this particular solution. And there'll be more solution in the future. A relevant animation tab shows what the SL model is all about. And of course, in the discussion link, you can post a comment, etc. So let's go launch the test calc by clicking on SL test calc tab. You'll see a complicated looking interface. By the way, you have to run Firefox or Safari that supports Java, and in this Lego you may have to click on Java allow now to run the test calc in case it doesn't appear here. So as you can see, the state panel is the default panel, and there is another IO panel. There are several other little bells and whistles. We can neglect those right now. Important thing to understand is that a state is a collection of properties. Each property, many of them you're familiar with. Pressure, for instance, P1, because state 1 is selected, unit appears here. So each property is similarly described. By clicking this checkbox, you enter into the input mode. But first, you have to select your fluid, which is liquid water in this case. And now we can enter properties of state 1, the inlet state. 100 kPa was given, temperature was 30 degrees Celsius, velocity, see the velocity was initialized to 0. You have to first click to initialize it and then click again to enter the input mode, and the height I believe was 0 meter. Mass flow rate is not given, but however the area is given. It was 10 centimeter diameter, so we can use expressions such as pi times 10 square, 10 to the 2 divided by 4, but that will be centimeter square. So we select centimeter square here and click the calculate button or the enter key to get the complete state calculated. If we go now to calculate state 2, you click here, get to state 2, or you can directly select it here. By the way, to go back to state 1, you can see you can select it back, or you can just incrementally go state by state. So let's go to state 2 and enter what is known. I believe the pressure is given as 5,000 kPa. Temperature is given as, we can go back to the example problem here. Temperature is given as what? 30.2 degrees Celsius. So the temperature rise is very little, and the pressure rise is very, very significant from 100 kPa to 5,000 kPa. The velocity from 10 to only 15 meter per second, and height from 0 to 5 meter. The exit is a little bit higher than at the inlet, 5 meter higher. Mass flow rate remains constant. It is given in this problem, equals m.1. So we have enough information. Now suppose you want to enter something else. Suppose I want to enter area. Notice you cannot. Even if you click here, it will tell you that it will not allow you because enough information have been already supplied. So we hit the calculate button to find state 2. The rest we can go to the IO panel and find out the change in the flow energy. J is the flow energy, J2 minus J1. So this is the answer. 459 kilowatt is the change in the rate of flow of the transport of flow energy between the exit and inlet. Now, to see how much pressure change is responsible, we can go calculate a state 3 and say, the pressure changed to P2, however the temperature didn't change, velocity didn't change. See how am I entering this information? I'm saying velocity at 3 same as velocity at 1, height at 3 same as height at 1, and of course mass flow rate did not change. So we found a state 3 now, the only change being pressure, nothing else. So that will tell us the flow energy changed because of what is the primary reason. You will see the pressure, the change in pressure is probably a big responsible factor in this case. Oh, sorry, no, we forgot, it is not m dot 1 star J3, not J2. I made a mistake here. Look, the change in pressure is a very big component, 384 out of 459. So likewise, you can see that the temperature change, you can to understand the contribution for temperature change, we can very quickly do similar way. P4 doesn't change. Temperature on the other hand has changed to T2, and everything else, velocity remains same as velocity 1, height remains same as height at 1. And what is the contribution to that? So this is state 4. So m dot, if you calculate the change in flow energy now, m dot 1 star J4 minus J1, we made a mistake. J4 has not been calculated because we made a mistake in our Z4 should be equal Z1, and m dot 4 we forgot to say equals m dot 1. Now the state J has been found, so therefore we can calculate J4 minus J1, and that's 65. So a significant portion of the change in the flow energy is contributed by this 0.2 degrees Celsius change in temperature. You can likewise show that the change in velocity and height has very little contribution. The majority of the contribution come from the pressure change 384 and temperature change 65. There are many other features that will become gradually obvious. It will be brought out in the future examples. One for a particularly nice feature is that if you now change, say, the working fluid to oil, you don't have to repeat all this calculation. All you have to do is to hit the super calculate button. That is going to recalculate every state. So every state is now consistent with oil being the working fluid. And in the IO panel, you'll find detailed output, state by state properties, detailed state properties, state 1, 2, 3, 4, etc. And a few lines of code known as test code. If you copy this and save it in your favorite word processor, later on you can just paste it back in the IO panel and click the load button to regenerate the solution. So this is a pretty nifty feature of test. I will stop here, and in the future videos I'll bring out many other features that this simple TESTcalc possesses.